darles la bienvenida a este seminario que nos va a dar el doctor Robert Nowack, quien es profesor emérito desde el 1 de enero de este año. Está cumpliendo 3 meses como profesor emérito de la Universidad de Purdue. En la Universidad de Purdue es una de las universidades importantes del centro de los Estados Unidos. Está cerca de grandes universidades y es una gran universidad por sí misma. El doctor Nowack se graduó en física en la Universidad de Wisconsin y ahí con honores. Y después hizo su maestría en la Universidad de Stanford, donde obtuvo la maestría en geofísica, y trabajó en compañías geotécnicas en San Francisco y tuvo una estancia muy importante en el USGS colaborando con Bill Ellsworth. Y después fue al MIT, en donde fue estudiante de Aki, hizo su doctorado en MIT con el profesor Katie Aki, uno de los sismólogos más importantes del siglo XX, quizás el más importante del siglo XX. Y él hizo ahí estudios sobre teoría de rayos, haces gaussianos, y se ha especializado en geofísica y en tomografía. Hizo también una estancia postdoctoral con el doctor Nafi Toxos, y pues nos congratula que esté por acá. Hemos tenido la ocasión de interactuar en distintas ocasiones, incluso en el aniversario de Ru Shangwu. Él pertenece a una generación de sismólogos, a una camada de sismólogos muy importantes en los Estados Unidos, en MIT. Así que es un honor para mí. Welcome to Mexico City. We are also pleased that estamos agradecidos de que aceptó participar en nuestro posgrado de Ciencias de la Tierra, dando una parte del curso de sismología avanzada, la parte de teoría de rayos y gases gaussianos. Así que él va a estar aquí todavía mañana, da una clase, y ya después pues lo llevamos al aeropuerto. Bob, welcome to Mexico. You have the word, you have all the privilege to use this stage at the Institute of Geophysics. Is the Auditorium Ricardo Monjes López.
Hello? Yes.
But you have to speak to the phone.
Okay. Because it's being recorded for their people here.
Please.
Now Paco asked me to give some lectures on ray methods, which I've been doing for the last week. And again, all of these courageous students who are sitting through these lectures, and I have one more tomorrow. But this was just an overview of, again, signals, noise, correlations. And with all the things on interferometry now and on ambient noise, so this is sort of a bit of review, but it's kind of my own version of the same material. So next slide. Okay, and here's just the topics, and I've got 4 topics that I'll be discussing today. The first one is the overview. Oops, and I think I can point, but the first one there is just an overview of seismic noise correlations and interferometry, but for body waves, because usually if you're doing this here, then usually the surface waves are the easiest ones to see. And the next one
is Chinese technology.
Yeah, and the next 2 here are basically an array that we set up in the central US, one to measure anthropogenic sources of wind turbines and trains and things like that. This is surface waves, but we also had recorded teleseismic waves at this array for looking at P-wave coda interferometry. And so those 2 are kind of from sort of a similar array that we're currently analyzing. And then this one, Paco wanted me to add this in because there's something called Marchenko imaging, which became very famous several years ago, particularly in the exploration geophysics circles. And I call it interferometry 2.0, but I think Paco would disagree with me on using that term. So next slide. Okay, this is the first section. Next slide. Okay, in the 1950s, Aki investigated ambient noise from vehicle traffic in downtown Tokyo to image shallow site structure. And Aki's work was later identified as an early application of seismic interferometry and by Sanchez Esma and Campillo in 2006. So really a long time before people sort of identified that his early technique was indeed seismic interferometry. But in the more exploration circles, John Claerbout was involved of how to take a transmission seismogram and convert it to a reflection seismogram by autocorrelations. And I'll be kind of emphasizing that here. So basically in seismic interferometry, ambient seismic noise can be used to form seismic images of the subsurface. And for body waves, in some circles of this whole wide discipline, because many people are doing this now, it's sometimes referred to as daylight imaging. Because if you have a room like this and with all the lights off and then light coming in from a door or something, you can still see because the diffuse waves have bounced around the room, etc., and your eyes can still form an image from that. I should just make a comment from Aki that Aki did a very humble thesis for his PhD. And later he would sort of apologize for this and say that, after doing this of just measuring traffic noise in Tokyo, he had no difficulty working on small topics as long as he himself was interested. But he was criticized in that in his day. Next slide. Okay, this is a fellow, Richard Weaver, who Paco and I both work at. Richard is at my neighboring university, University of Illinois, and he was the one who really identified in modern terms that you could cross-correlate ambient noise at two locations and form essentially the Green's function, as if you could take one receiver, turn it into a source, and record it at another one. And here's a picture of Richard here. He may be in Mexico City in the upcoming year because of working with Professor Sanchez Esma. So next slide. Okay, so some things should click it a few times because, okay, and then again. This one, I should not do that. Okay, so the idea here is that you have lots of signals coming around in the earth, vibration signals. And the question is, can you reorganize these signals into a coherent experiment? And in many cases you can, but there's still lots of challenges on how to do that. So again, I just note this here, that one of a receiver here is suddenly kind of like a neutron, a neutron converted to a proton or some such. So that's kind of what this is going on. And Richard Weaver was really the first person to identify this, and then worked with people in Grenoble in France to develop this in the early 2000s. So next slide. Well, this is famous, and this will separate if you're an expert on interferometry or not. If you've ever been able to see Richard's block of aluminum that he was working with in his lab at University of Illinois, the idea is he would have two receivers on the surface, and he would just cross-correlate the signals and compare with an exact signal from one to the other. And it had sort of an oblong shape, and it had a hole in the middle. And I was privileged a couple of years ago to see this sample, and just from his history of seismic interferometry is of use. But then he tried to calm down the sample by isolating it more and more and more to where there was just phonons in the sample was enough to generate this effect. Next slide. Okay, so seismic waves beneath the receiver can be retrieved by converting to a co-located virtual source and receiver. So we have one receiver now, and I'm going to co-locate it as if it's simultaneously acting as the virtual source and receiver. And so this can be done with interferometry of ambient noise to construct an effective zero offset reflection response for a virtual source at the receiver location. Next slide. Okay, and this was our first attempt of trying to do this, of just sort of autocorrelating lots and lots of data for a coincident at a receiver. And the question is, can you sort of get this from hourly recordings? Can you get this from weekly, monthly recordings? And this is months over a year. And this is basically a synthetic seismogram to compare with what's coming out of this. And again, it's still a challenge because ambient noise, as we well know, has lots of surface waves. And again, with the coincident source and receiver, the idea is that you could hopefully emphasize more of the body wave signal. But this elicited a great deal of excitement and interest in autocorrelated signals, more in the level of what John Claerbout was thinking about here. So next slide. Next slide. Okay. Well, this is just an example of a very nicely instrumented basin in Spain by Romero and Schimmel. And they did this right after our paper. And so they immediately went, this basin had all kinds of well logs. And so they knew it really, really well. And so they did this game of doing the autocorrelations. And we're comparing with models and synthetics with the data. And it reasonably mapped out reasonably well. Again, it is a challenge doing this because the ambient noise has all kinds of other signals in it as well. Next slide. Well, even the people at the InSight mission on Mars did it, because if you only have one sensor and very few Mars quakes, what are you going to do? And so Dangan and Levander in 2020 essentially made an equivalent reflectivity of Mars using this. And again, after that, this is the difference in the United States with these big NASA missions. This only has 2 authors, but then after that, there was 3 or 4 papers that did this with 20 or 50 authors, because it's all the NASA people getting involved. And I don't know about you, but I have a very difficult time knowing who to identify as the principal authors when you have 50 authors on a talk. But this only had 2, and it was the first for Mars doing this effect. Okay, next slide. Okay, the conclusions here is seismic interferometry provides the possibility of determining reflectivity where no active sources are available. But the problem, again, is that there's body waves and surface waves. And if you've been doing this yourself and cross-correlating, the surface wave easily comes out. You really have to work to get the body wave signals. And I just note this here, in the 1940s and 50s, the industrial community attempted to isolate P-wave reflectivity from everything else from their signals. Now, they had active sources, but they had to get rid of surface waves. They decided P waves, and in fact, S waves should dominate in reflectivity in multiple scattered media. And they did everything to get rid of those as well. And so really, these provided the first detailed images of the crust. And the idea is, can you do this with daylight imaging? Next slide. And this is just an example you've all seen. This is a normal reflection seismogram where you can see echoes, you can see faults. Again, the challenge is, can you come up with images as good as this with ambient noise, in an industrial setting? Someone, Ruhl Snyder, said you should have trucks with square wheels that kind of kaplunk, 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 go around the oil field making noise, and then use that. But again, can one, in principle, the data's there, the noise is down there. The question is isolating it. And that's why I kind of put this into the thought process in my head. How can we duplicate what the people in the 1940s and 50s did to come up with, things? And then this is P waves. Should be S waves, but it's P waves, given how the data, how multiple scattering work. Next slide. Well, this is the second topic. The second and third topics are me putting out an array called autocore array and attempting to investigate the signals we're recorded. The big challenge here is this experiment was for 1 year, but it overlapped with COVID. And so I had to go out to these farmers' fields and retrieve data, come back where everyone was supposed to stay in their house, which was a challenge. So here's some of the wind turbines here. And so we're going to use interferometry to help us, but this will be easier because I'm going to be looking at the surface. Okay, next slide. Okay, next slide. Oh, there we go. Okay, this is the experiment, and it's about 30 kilometers from here to here. And then these little red dots here are wind turbines. But the wind turbines go way up to the north. There's huge numbers of them up there. And here we are with respect to Chicago here and the Great Lakes, et cetera. And and I wanted to do this to kind of originally, help me out by getting rid of surface waves initially from this kind of spiral array down here. And I had extra stations, so I ran it up to the wind turbines to the north. And so, okay, you can, next slide. You can go to the next slide. Okay, and this just covers what it is. Roughly 30-kilometer north-south array for about a year. It had this spiral array to the south because I wanted nice azimuthal coverage for beamforming. And I did this, but I'm not going to be talking about this here. To the south of the array, there is an east-west train line. And I thought, oh, I'm going to use those trains as sources of opportunity. And I really didn't think about these wind turbines much until they tended to dominate the signal on the whole array. So to the northernmost stations are within a large wind turbine. There are local roads in the area, but we studied this late at night and early in the morning to kind of reduce the effect of vehicle traffic. But we're wanting to look at that too. We are looking at that. Next slide. Okay, just to give you a perspective, and I didn't actually fully realize this because this is right 15 kilometers away from my university. There's a huge wind farm, and that wind farm is Meadow Lake, and that's the one to the north where my array is located. There's one kind of off to one side called Fowler Ridge, and both of them have more than 1,000 wind turbines. And in fact, we knew the people at the banks in Indianapolis who funded putting these out 20 years ago. But it is surprising for us to realize that the two in our neighborhood are two of the top 10 biggest in the world. And so those stations further north of my array make up 1,000 wind turbines to the north. Just to give you an example of gigawatt power, the Meadow Lake is 0.8 gigawatt. The one nearby is 0.75. But then if you look at China in this Gansu wind farm, 20 gigawatts. So they're going into this big time for wind power, okay? So next slide. Well, I, being stupid, thought, oh, I'm gonna follow the trains because I have 2 trains, freights that come south of my array twice a day. And I thought, okay, I'm gonna try to isolate those signals, use those as sort of signals of opportunity if you want. But then here are the wind turbines to the south with a couple of our stations there. Next slide. Okay, so this is again, trains versus wind turbines. Which one will win out? And I was away from the train track. And it turns out they just didn't propagate far enough. They went maybe 8 kilometers away, but not enough to give me the full 30 kilometers of the array. So when I took a station at exactly the same time and did exactly the same analysis. Next slide. Okay, this is halfway up my array, and suddenly the pattern completely changed. I get this type of spectral peaks and this type of spectral. So it in no way looked like the train. And so the question was, what were these things? And so we had to think about, first of all, for us, what are these resonances? And so we had to do some analysis for that. Next slide. Okay, trains versus wind turbines. And again, ST12 is further to the north. The train signal can't be seen. We see this other signal. And again, we get these large equally spaced spectral peaks, approximately 1 hertz separation up to about 14 hertz. And it turns out all the stations from 7 up to the end of 16 all have that signal to them. Next slide. Well, we were very lucky. The first thing we thought was soil resonances, H over V. So that's what we were thinking. That's what we're seeing, right? We were fortunate that someone in our state had gone all over the state making shallow refraction measurements. So we have 19,000 shallow refraction measurements across the whole state. And this is just a small area, and they did it for 30 years. So we had to get this data from them. And here's our stations once again. Here's the east-west train track. And then I don't have the wind turbines, but they're all up here. And so, so we want to see what, from these, we could just see what the soil depth is. And in this area, it's a glacial area where it's glacial tills over pretty hard rock underneath. So you get a good, reflector on there if you want to. Next slide. Well, this is the thickness, and it goes anywhere between 20 meters and 100 meters as I go from south to north on the array. So I've got a fairly wide variation in thickness. And the way I can think about this is you've got the underlying topography, and when the glaciers kind of retreated, they just filled it in. So some are thicker pods, some are thinner pods, and that's kind of what S-fin here is relatively thin, because we picked an area where we installed that EarthScope station. We wanted it relatively thin soil column for that site. Next slide. Well, we also had to do HVSR, and here is, I have to look at this to see, but the refraction depths are the circles. The pluses are OPSPI for a short time window, and then the stars are Mustang, which is the Iris Pascal tool for Iris stations. And so, and you can see they roughly match. And so we are getting a variability. The interesting thing here on the bottom is that, the refraction gives you P wave speeds, doesn't give you S wave. The refraction, the HVSR gives me, we have the thickness from refraction, and we can get at separately the VS speed because we have the refraction at the same site. Anyway, next slide. Well, we still need to know what these things are. And so this is at one station with different wind speeds. Now, we were fortunate enough to have a tool called Dark Sky, which Apple uses. And we have a number, roughly in the United States, every 30 kilometers is a national meteorology site. So you can get wind speed, wind direction, et cetera. And so we can then use this Dark Sky tool to interpolate to where our stations are. And this is at one where this is a low speed, a middle speed, and a high speed wind. And you can just see these resonant peaks develop. So this is, these peaks are something to do with the soil or some such. But it turns out we then got a negative result that, let's go to the next slide, please. Well, this one basically shows the development of the peaks at all my north-south stations. And what we found to our surprise was the major peaks didn't move. So if it was soil resonances, these would be moving with the thickness of the soil, and they're not. So our conclusion tentatively was that because they're not shifting across the array, this is a source effect and not a soil resonance. Okay, next slide. Okay, so locations of spectral peaks do not, and this is detective work. We're being Sherlock Holmes here. What are these things? And so they didn't vary with location, even to the most southernmost stations. And so we assessed that they were not directly related to basement depths and inferred that it was a source effect. Fortunately, we were reading lots of papers from the Germans on wind turbines. And it turns out those type of resonances come from the wind turbines, but they don't come from the prop. They come from the resonances of a 100-meter building with a rotating element on top. So it's rather tricky how these resonances develop if it is the wind turbines, but they do, and they look similar to that, depending on the height of the wind turbine. So the spectral peaks and the vertical seem to be source effects and not resonance effects of the soil column. Next slide. Okay, now we'd like to apply interferometry for our data. We're going to try to get kind of Green's functions between two stations of our array. And we're going to deconvolve them and have three kind of virtual sources, and then compare them with different wind speeds. Okay, so SFIN is on the very southern of our array, 13 is kind of mid-north, and 16 is the very top of our array. So next slide. Okay, so this is at a high wind speed. And we have basically, this is our pseudo source. And you can see the wave just moving down to the right. And it's roughly moving, given that we know the refraction data in this area. And it's basically a layer of till over hard rock that's roughly going at the Rayleigh speed. So this is our Rayleigh wave. It's pretty non-dispersive given the soil or the rock characteristics underneath for this site. But what happens when the wind speed goes lower? What happens is that this signal tends to kind of disrupt. So it's sort of wind derived, but it's wind derived, moving the wind turbines, and then them, at least in our interpretation here. But you can see something interesting. This would be a little wave going up here. This would be a south to north wave. This would be a north to south wave. If this was a fully diffuse field here, we would have equal energy coming from the south of the ray and the north. So this data is all coming from the north. Okay, so we're using interferometry, which shouldn't work here. We have no diffuse field at all, but we're using it to identify where the sources are. Okay, and if the wind speed goes down, the whole thing comes apart. Okay, as you would imagine it would. Next slide. Okay, this one, we put our source here, and this is high wind speed. So it's still coming from the north here, it's coming from the north here. If we go at a middle wind speed, and our interpretation here is all the wind turbines further to the north are not getting here, not giving as much power. So you're seeing this little cross here for me, and that's suggesting to us that at these mid wind speeds, the wind turbines right around those stations are more contributing. And then when we go to very low wind speeds, it just breaks apart. Okay, next slide. Okay, and this is SFIN at the far bottom. So our station is here at high wind speeds. The Rayleigh wave is just barreling down from the north. Again, our interpretation there, it is high wind speed, but it's from the wind turbines themselves. At low wind speed, or middle wind speeds, I have the wave going down. It comes up slightly here, so we're getting some north propagating signals here. And then when we have low wind speeds, it just breaks apart, but we're still seeing a heavily northbound signal. So I guess we were very disappointed here that the trains were not dominating these signals. If they were, the signals from the south come out. Well, these were windows picked where there aren't any trains. So let's find a one where a train is present. So next slide. Okay, this is where a train is occurring. And so in this window, we still have the signals coming from the north, but then we have the signals coming this way here. And this we're interpreting as the train signal going about 6 to 8 kilometers away from the train track, but by no means the 30 kilometers, okay? Now, I should point out why this is important for particularly this 30 kilometer stretch. The Germans were studying wind turbines because they have them all over the country, but they can't put sensitive seismic stations near them because they kind of mess up the signals a little bit. And their general rule of thumb is 15 kilometers. And we've got our array easily going 30, and it could go longer as well. So, but the difference here is this has 1,000 wind turbines. When the Germans were doing it, they had 10, and they're playing that game. And they had a 15-kilometer exclusion zone around where they put sensitive seismic equipment, okay? So let me move on here. Next slide. Okay, this is just these local spectral peaks developed as the wind speed increased. It didn't vary in frequency across the array, suggesting it wasn't soil resonances for that. The spectral peaks are attributed to the wind, could be observed for 30 kilometers across the array, but those resonant peaks we're thinking are the wind turbines themselves getting kicked into gear by the wind. And it wouldn't be necessarily the wind just generating the soils, because presumably it would be variable by the soil thickness. Okay, so except for the southernmost 6 to 8 stations, the signals propagating were dominant from the north. And let me see. And then we basically suggested that we could sort of isolate by the non-diffuse nature of these sources where they were as the wind speed went down. Okay, next slide. This is the fourth part. And this is one that after we did our paper on looking at just simply, autocorrelations at stations to get body waves, other people, particularly the Australians, were looking at P wave, P coda. And the idea is you already knew the P waves are coming from below. So you kind of know that they won't be, at least in that sense, contaminated by the surface. So we wanted to try that here as well. Next slide. It's the same array that we had before, but I'm going to then use these to measure teleseismic earthquakes coming out. So next slide. Okay, next slide. Okay, and this is just some events that we're using that were recorded for the year on this array. And we tried to avoid distances for PP or PCP or anything that could get into this window. And we picked events that were shallow or deeper than 100 kilometers, so we didn't have other phases affected. Next slide. Okay, and this is just OpSpy, where I'm just plotting some rays. And we are looking at directions where we're just getting that direct P wave signal. Next slide. Okay, this is taking that P coda window, autocorrelating it, but then you take the early part of the window, the center part of the window, and use that as an example of what the source time function is. Like in a receiver function, you'd use your vertical component. These are vertical components. And basically what I'm doing is I'm taking the near end part of the autocorrelation and deconvene that out of the other part of the signal. And I can see these pulses here, which I interpret as the MOHO. Okay, so that's a MOHO phase given the P wave autocorrelation. And again, it is, in one sense, you could think of it as a receiver function, but I'm on a vertical component. So it's not, sacrificing the vertical, to do it on the horizontal, which would give you S-waves. Next slide. And this is just another of a few earthquakes that we had. And we're going to try to identify those guys. And this delay distance away would be roughly how far this is from that signal. And with P wave, it would be the wave going up to the surface, reflecting off the MOHO and coming back up to the surface. Next slide. Well, we'd like to try that. This is the autocore array, and this is just a bunch of stations along here. And I have better stacking capability on my 18 stations here for that, but I want to compare across a bigger array. So next slide. Okay, so this one is, we have models, and there are many of them, but it turns out, let me see, the crosses are converted to time, echo time, 10 seconds, 12 seconds, from crust 1.0 across the central part of the United States. And the circles are kind of the closest positive wiggle of the data that we're getting here. Next slide. Okay, and this is another event. And you can kind of see that, at least if you pick your eye of where you think that is coming in, we're at least tracking what crust 1.0 is doing. Now you have other things going on in here, and that's the idea, is that you'd like to do crustal. You'd like to see stuff in the crust, and there may well be stuff here, but we haven't attempted to analyze that here. Next slide. Okay, this is just, we're recording P wave coda. We know the waves are coming from below. We don't have surface wave contamination, and we can play this game. I want to do the vertical component. I don't want to sacrifice it in a traditional receiver function. And we sort of can get this to work. And this was done by the Australians at ANU when I was about doing this with the full noise field, and somehow got it to work on that very early slide. Okay, next slide. Okay, the last thing is a topic, this is for Paco's benefit, of seismic interferometry to a relatively hot topic these days called Marchenko imaging. So go to the next slide, or next slide. Okay, So the idea here is, let's say I've got sources and receivers, and this is kind of exploration that are people that are doing this right now. And that's kind of in the picture there, but it doesn't matter. Let's say I've got a scattering thing I want to find oil or something like that. And I've got a very complicated overburden here. The idea is, can I essentially take those sources and redate them down here underneath a complicated geology so that I can get a better snapshot of what's going on here. Now, in traditional migration, if you like to think about that, they would have things of layer sinking experiments where these sources would go down into the earth, these receivers would go down, and then you would kind of cross correlate them in an imaging condition to get a beautiful picture in reflection seismology. But really, from my point of view, Marchenko imaging, where Marchenko is a famous quantum scattering guy, kind of put all of that into a much clearer theoretical background. Next slide. Oh, wait a second, before you stop, let me know. So you could put a source physically down here. We could, in classical interferometry, I might have a well down here with receivers in the borehole or something, and I could turn one of them into a source and one of the receiver. So I could do it with classical interferometry. But the question is, can I use Marchenko imaging to not have any sources and receivers below? You're entirely working with what you have on the surface. Next slide. Okay, so that's too many things in here. This was basically the receiver function stuff, but it needs interferometry needs sources all over the place, or you need a diffuse field in principle, although I'm playing with cases that I'm not worrying about that. But in the Marchenko approach, I only need one side illumination and not illumination everywhere. And that's what some of the exploration people are playing with right now. And also the virtual source does not have to be located at a receiver. And so if one only has one side and stuff coming from the surface, not over a big sphere of sources coming in to do classical interferometry, the question is, can we do this in this setting? And in a certain case, you can. And this mechanical engineer did this initially. And then these guys actually at Colorado School of Mines were the first people to do it then. Next slide. Okay, this is just an example here. I have a few minutes here, but let's say that I've got a scattering object here, and this is the scatterer I want to find. But I want to redata my experiment down here so I get a good look at my oil-bearing reflector down here. So that's sort of the simple-minded way to think about it. And I'm just trying to play with the Marchenko imaging so I know how it works. Next slide. Okay, the idea is if I have a source, let's say I've got receivers down in depth, and I've got a wave coming down, and this is really a VSP. But again, if I had receivers down a borehole, I could get this, and I hit a reflection, and it will bounce back. I get multiple reflections in there, and then this might be from the very lower reflector, right? But classical interferometry needs it all over. So it means I have to have something coming from the bottom as well. So I need this too. So what I want to do is I want to refashion those as if I had a source in the middle of my layer, in the middle of my zone, and just using this data. And that's what Marchenko imaging kind of lets you do. Next slide. Well, this is a physical source of 2.5 kilometers with some data. And this is with interferometry with sources coming from the top and coming from the bottom. I can refashion that data to make another record section with a source now in my borehole. And usually boreholes don't like to put sources because it'll blow up the borehole and you don't want to wreck a $50 million borehole. But the idea is I can do that without having a source in the borehole, and I can simulate. Now you'll see that there's a slight shift here because this is sort of, there's negative times and positives times. And if I shift this slightly, it looks like that. But now the question is, can I do this without the sources coming from below? Okay, so next slide. So this is classical interferometry. And so next slide. This is Marchenko dataming where I get exactly the same thing. So I have nothing coming from below, only from top, one-sided illumination, and I get the same thing. Okay, next slide. Okay, Marchenko only requires one-sided. The virtual source does not need to be located at a known receiver, and also a detailed velocity model isn't even needed, okay, to do this. So, and in 3D, there's some more elaborate restrictions in doing it. Next slide. Okay, these guys even extended it where I don't even have to have receivers in the subsurface, nothing. And I can make the same thing. So if I go to the next slide, or next slide. Okay, this one is a VSP gather, where as if I have receivers here, where there are no receivers in the borehole. All we have is surface data, and I've manufactured a VSP without anything in the borehole. And a borehole costs $50 million. So if I can manufacture a vertical seismic profile without any sources or receivers in the subsurface. But if you think about that, that's what John Claerbout was doing with his imaging conditions. He had sources on the surface, receivers, and he layer sunk them down into the earth until they cross-correlated to make an imaging condition. So, and that's why I was saying this puts that into much more better theoretical foundations of what's going on. Now, the Dutch who are doing this in the Colorados are doing this in laterally bearing models. This is just simplified. Okay, next slide. Okay, this is just to show that all four of those give essentially at one position, give the same size. So I can do it with a true size, a true source at, oh, this is at 2.7 kilometers with, I guess, a source at 2.5 or something. And it basically gives all the same seismic with less and less information right in the borehole in the earth. Next slide. Okay, and then you can actually use that to come up with a model of the earth. And this is the true reflectivity of the earth, a kind of impulse. And then this is what's coming out of doing the marching. Okay, next slide. Okay, so focusing energy to points in the subsurface without knowledge of the specific velocity model has a lot of potential for imaging. Also, this approach has the capability of separating up and down going waves in the interior, and that gives you imaging potential. And I did note here that when Claerbout moved away from 1D scattering, he used this framework to layer sync his sources and receivers into the earth, and then cross-correlating them, which is called the imaging condition, to make a snapshot image of the inside of the earth. Okay, and I don't want to go through, well, except that the advantage here, he had to break out of 1D, he went into Born scattering, which was single scattering models. And with Marchenko, it's purely multiple scattering. So you have a lot more information in a multiple scattering regime, which are typical, if you've ever seen a reflection seismic event, that's single scattering. Okay, they've taken out other stuff. And maybe that's good for looking at the image, but that's how it's set up. And this isn't how it's set up with Marchenko. Next slide. Okay, I just have a last quick thing here. This is to try it with some data. And Professor Sanchez-Sesma and I was commenting about, you can't show those theory slides without showing some data. And this is a carbon sequestration experiment in Texas. And they have a bunch of surface sources with receivers down the borehole. And some parts of the borehole have more dense receivers, some have less. And the question is, can we kind of find the injection point of where they're putting the CO2 by doing this Marchenko stuff? You can do it with VSP processing, and people do it, but there's some advantages to trying this with Marchenko. So next slide. Okay, well, this is a synthetic case, and the idea is here's some model, and here's like receivers down in a borehole, conceivably, and you set up sort of a VSP model. This is all synthetic. And what I wanted to do for a more complicated model is, can I redatum a source somewhere in here from just this data? So next slide. Okay, and so this is a physical source on the computer here. This is a redatum source from the surface data. So I can move the things. I'm kind of rearranging my data, if you want to do, and this allows me to rearrange my data. Okay, next slide. Okay, and then I can essentially invert for the reflectors here. And this is pre-injection, this is post-injection of the CO2, and this is a different plot. This one basically, if I go to the next slide, so it's pre and post to try to find the injection zone. So I'm imaging the pre-data, the post-data after injecting the CO2, and then I want to see if I can find that, okay? So this is just synthetic. Okay, next slide. Okay, this is real VSP data on this. And again, it's got pretty dense coverage for some of the array, of the in depth in the borehole. But this is the thing we can compare with VSP processing with Marchenko processing. Next slide. Well, this is kind of a summary plot, but B here is the reflectivity obtained from Marchenko imaging, and this is from VSP, and they essentially overlap. But essentially, the Marchenko has a lot of advantages in terms of what it requires. And in fact, it doesn't require very many receivers in the borehole at all. And I can simulate with the VSP with receivers in the borehole GIF. Okay, next slide. And this is just our before and after plot. That's the zone of carbon dioxide injection. And the black one, I have to remind myself what it is here. That's the pre and post Marchenko, and this is the VSP, and that's their overlap. And I guess, and we kind of know where it is because this is these dotted lines, but I have a bit more symmetric pulse here than the VSP process. Anyway, next slide. Okay, Marchenko imaging of a carbon sequestration zone compares well with standard VSP processing, in fact, very sophisticated VSP processing, and can find the known sequestration depth for the carbon dioxide. And however, Marchenko imaging only requires a limited knowledge of the velocity model, which you have to get for the VSP. You have to do that with the first arrivals first to get that. Marchenko doesn't need that. And then it does not require a dense set of receivers at all inside the Earth or in the borehole. And in the furthest case, no receivers in the borehole. So if a borehole costs $50 million, you might be able to duplicate a VSP with no receivers in the subsurface or even a borehole. Okay, next slide. Okay, this is just overall. So my timing is pretty good here. I've taught for so many years, and I don't even want to even say how many years. We've got sort of some senior faculty here. If I gave you a day, the students would scream at how long I've been doing this. But at my university, they're 50-minute classes. And for you guys, I'm doing 2 hours because that's how Professor Sanchez says let's set it up. Usually 50 minutes is enough to fill up the brains, right? But I always have to finish a lecture in 50 minutes, and I'm right now in pretty good shape for that. So this is a really old picture from Kees Wappener from Delft University. And the idea is if you have some smooth model from, say, travel time tomography, you really want to get a more detailed image. And the idea is for all of these new interferometric techniques for body waves, you want to make something that looks like the bottom versus the top. Now, what Kees Wappener really did here is he did kind of a standard image of an oil company synthetic data. And it's a little fake, but I still like the idea. However, the French have sort of started to been able to do this now. And the next slide is from Grenoble. And so next slide. Well, this is travel times in the whole Earth, a synthetic model. And this is entirely from ambient noise. Now, in fact, there are tricky things here. And this is a little bit old. This is 2013. But the idea is that you see some phases in here. This one's here, this one's here, this one's there, but it's kind of not in here. And so it's not maybe that the Marchenko's right, but they're trying to find biases and artifacts in doing that. And if you can do it for the whole Earth, then the idea is for a shallow, and then you can ideally image this for a model for the whole Earth, which you can do with these models with just arrival times, etc. But in the shallow Earth, it's a little bit trickier because you're so dominated by those surface waves in the near surface, and you do need to get rid of those, and you have to simulate what people in the 1940s and 50s in Russia or United States or oil companies did to make those beautiful reflection seismographs. Okay, and I think that's it. Next slide. Okay, thanks for your attention. So several different topics. On any of those that you're interested in.
Preguntas aquí abierto.
Some of you are doing ambient noise, so I don't know who's doing. Yeah. Now, I think we're only using the microphones for anybody. So we don't need it for you guys.
Thank you. Very nice your presentation.
Is that on?
Yes.
Okay, good. Okay.
Are we able to retrieve some converted phases, such like P to SV, by using horizontal components? What do you think?
I was using a vertical on that 2017 paper, and we were getting P to S conversion. And that was highly controversial because if you had something that was waves going down and up, if it's just 1D plane waves, you get no conversions, right? But the way I rationalized that I was getting them is the waves that are kind of at oblique instance, you know, if you break things into plane waves, will leak into the vertical component. So in fact, even for a vertical virtual source, you know, we have things that look like the PS conversion on the crust.
Okay, because you mentioned that the vertical components autocorrelation can be managed as receiver functions, but by using, if I don't.
Well, what we're doing is a trick here.
Yes.
We're calculating autocorrelations, and then I'm talking about the middle part of the autocorrelation function as being sort of representative of a source time function. And then I'm cutting that out and I'm deconvolving that from the rest. Okay, so we're in a traditional receiver function. You've got a vertical component, an SV component, and you're using your vertical component as if it was the source time function. And you're deconvolving this. What I'm doing is I'm taking the near part of my autocorrelation, calling it my source time function, and using that to decon. And the benefit there is I can get a vertical component receiver function. Okay, so and sometimes that's of use if you want to get the Poisson ratio, or you want to get a VP and a VS for, you know, your structure.
Okay, yes, that's a nice and interesting topic, because I want to explore this kind of topics about the continuous monitoring of autocorrelation with both vertical and horizontal components.
Sure.
In order to investigate if there is possible to monitor volcanoes or geothermal.
Sure. Oh yeah, the monitoring aspect. This is where in interferometry, people in optics and stuff were trying to get much more detail than you could on the raw signal. So if you're interferogramming stuff, you can get, whether it's, you know, whatever field you're doing, you know, you can get better resolution, and that's the whole intent. So you're looking for very slight changes in the subsurface, but that's a whole other discipline than what I'm doing here.
Okay.
Yeah, but it's really, really neat. You know, can you see stuff in the interferometric field? But somebody told me this in an odd way. They said, if you look at seismology and you look at even exploration seismology, our data is so good that we can use raw waveforms. In most areas like acoustics or even optics, everything is well, in optics, it's just the intensity field. But in other fields, in acoustics, you may only have cross correlations and signals, okay? And so we're kind of going back to where other disciplines realize that correlated fields are quite useful in many different ways. But again, I only envision it that we have very good amplitude and phase of raw seismograms. And yet we forget about the fact there's a lot of terrible data out there in other fields like acoustics that they must autocorrelate data or cross-correlate data to get interpretations. I mean, think of an acoustic and you're by a train or something, you're listening, you know, cross-correlating actually compresses signals. You know, you have long bits of noise. You don't want all that noise. You want to compactize it, right? And so there's all kinds of benefits of doing that. So resolution analysis and stuff. So the question is, why don't, in migration analysis for oil industry, why don't they use cross-correlated fields? And I do have a paper on that, but it's early, just on migration, imaging of, you know, oil company kind of data.
Okay, can you share your paper?
Yeah, I can do that. Sure, I'll give it to Paco, and he can refer to it. It's old, but the people that are the experts on this are the people in Delft, in Kees Wappener, and all of those people, you know, plus Roel Sneeder, who's also Dutch, in Colorado School of Mines.
Okay.
Yeah, so.
Thank you so much.
We have time for at least one other question. We're right at the hour. So if anyone else has a pressing question.
Is there another question? Otra pregunta?
And I apologize that this is in English and your minds are working in overtime to do a translation, a real-time translation in your brain to understand in Spanish. So my apologies.
No, they're already well trained.
They're well trained. Their neural nets are well trained in the brain. Everything now is neural nets, by the way. So you all should be taking a deep learning course if you haven't already, because it's
I have a question now.
Yeah.
Once you identify that the spikes you have in your experiments are source effect, did you succeed in eliminating and exploring what happened with this with the signals? Can you eliminate, or there were too many peaks?
Well, the difficulty is you really need to flatten. Now, we identified they're there, but then we had to do everything to flatten them when we did the interferometry. So that's the dilemma. The interferometry does not like those big spikes. They want something that's uniform temporarily. They don't want spiky things in the frequency domain.
Okay.
So we bring those down to do those interferometry plots.
And another question regarding Marchenko, still you need a preliminary model, isn't it?
No, not in 1D.
Oh.
And that's what this guy Rose at this Iowa State lab, an acoustics guy, was saying. He could have an interval where he had nothing. He wouldn't even know what the velocity model in, and you can still relocate it to the correct location. It doesn't need, but in 2 and 3D medium, you need a very approximate average smooth model to essentially go between the imaging point and the surface.
I see.
And kind of, you think of it with seismic migration. You need a smooth model first, and then you're imaging your reflectors in there. So on 1D, it really comes out like magic. But in 2 and 3D, you need a smooth model background. So there is a pre-processing step needed.
Okay.
But nobody thought that. So what Roel Snyder and Kees Wappener did is they took something in 1D, which is traditionally Marchenko integrals, and pushed it into 3D, and it worked. And usually people are not that lucky, because usually you have to work out the mathematics first. And that's the brilliance of both of those two guys. And it's not that both of them are not great mathematicians. They are. But Roel has this intuition. Kees will justify it later what Roel came up with. You know, so they make a good team. You know, so.
Thank you. Is there another question? Hugo?
Anybody?
Well, just give it a big applause. Professor Nowack.
I should say, for anyone interested, I do my last Ray method lectures on Thursday. So I hope I haven't scared anybody off on my Ray lectures before. They were supposed to be elementary. So, and this one will be be a little more intricate on Thursday.
Ya tenemos mañana da clase de 10 a 12 en el edificio 18 del Instituto de Ingeniería, debajo del edificio 12, a las 10 de la mañana. I make the advertising already. If someone wants to get us, there is, I think there is room.
The interferometry for surface deformation is very high art right now, and so it's I call it just a parallel field, but has a lot of great applications these days. Modeling the deformation after an earthquake, by interferograms, and it's the same conceptual stuff, but just different application in neurosciences. So, for those that do that, I don't know if anyone's doing interferograms for imaging fault ruptures, etc., after an earthquake, but it's just fabulous stuff and getting way down to centimeters resolution. Amazing stuff.
Muchas gracias, Bob.